Hi, my name is Shannon Bradley. I am a shift supervisor of the High Flux Isotope Reactor, which is part of the Oak Ridge National Laboratory.
Hi, I'm Patrick Bronner. I'm a seasonal engineering intern at Guadalupe Valley Electric Cooperative.
Hi, I'm Jamie Curtis.
Smollett. I'm a protection and control technician for AEP Texas, and I live in San Angelo, Texas. The distribution grid anomaly detection project is a fancy way of saying we find faults and we tag them for distance and nature and type of the fault. The goal of this was inspired from our conversations with several different utility companies that indicated to us that they don't actually investigate faults unless there's significant damage done along the lines. We thought that was problematic at times because there could be some sort of issue building that could eventually cause damage to equipment that could be prevented by investigating earlier. So one of the main things what reported to us was that investigating these faults that didn't cause any damage was too time consuming and costly to check into the line to the faults. And this was especially true in more rural utility companies because they felt like there was more line per employee to investigate, so it just was not very cost effective. The capability already exists in some niche markets, but is not widespread in the industry because most of our country is in fact, rural. There is a clear need to provide some way to easily analyze this fault data and potentially provide that information so that they could more quickly analyze the information and get to the fault and investigate specifically what was going on in that area. The intent is obviously to speed up the investigation process and even automate portions of it if we can do that through the analysis of the fault data. And the additional intent is to compare fault data with historical data to try and predict the type and nature of the fault. And so that can be as simple as a line-to-line fault, line-to-ground, through-phase balance, or even more in-depth is to say maybe this was a tree strike or an animal strike or some sort of auto accident caused damage to the pole, something like that, to get a little more in-depth knowledge from the data. The third thing we would like to do is to use modeling to predict the distance from the fault to the nearest sensor along the line. And this was communicated to us to be of particular use to a lot of these companies because if we can provide the distance from the fault to the sensor to the utility companies, that at least gives them a starting point to investigate. Our requirements are pretty simple. We want to, at a minimum, to have the necessary information to speed up the investigation process. We want to predict the potential causes along with probable distance from the sensor, and it needs to remain cheap so that it's affordable for all utilities. Like I said, these are a lot of the companies that we were talking to are rural companies that don't have the same bankroll as some of the larger companies. And we cannot compromise sensitive information held within the default data. So a lot of the default data obviously has locators and stuff like that, so we can't have that information getting out. So we'll have to cleanse the data so that if we put it and store it outside of their system, that it doesn't have any of that information. And that goes into some of our stretch goals, which are the next little section. Our stretch goals are goals that we would like to get to if we can towards the end of the project. Once we've gotten everything else got squared away, if we still have the time to work on some things, we would love to do that. And two of our big stretch goals are we would like to add some sort of cloud storage so that we can actually store all this historical data that we referenced and kind of compile a big stockpile of data that can be used to analyze and just kind of improve our AI analytics. And then another way of doing that would also be the implementation of pole-mounted sensors to provide increased data accuracy. And it's more sensors in the area, so it can't be bad. So our problem statement and our customers. Much like we stated in the last slide, many of the utility companies that we talked to initially to seek ideas for our design project communicated to us that they had trouble when it came to figuring out the source of faults and nearly all near fault events. And a near fault for us is not an industry term, but rather a term we use within our team to describe a condition that causes a temporary spike in power that could be attributed to a fault, but is not long enough in duration to trigger an operation. So either a recloser is able to close it quickly, and there's no damage, no reason to investigate it from the utility's perspective, and at least historically, and or it is just a large spike and it isn't even significant enough to cause a trigger. And it's very important for our project that we keep costs to a minimum to be able to provide the highest possible quality of analysis at the cheapest price. Our target customers will be small co-ops and other small power distribution companies around the country, and they would not normally have access to this kind of data. It is very important for our project that we keep costs to a minimum. No. It is very important to our project. No, it's very important for our project that we keep costs to a minimum. This is mainly because our target customer for this project are smaller utility companies, co-ops, rural companies around the country that don't have the same budget as some of the larger companies. So if this turns into a very expensive prospect, then it's going to kind of alienate a large portion of the utility companies that we're trying to target with this. That's not to say that we wouldn't want larger utility companies, but we don't want to exclude. It's important that we don't exclude the smaller companies that can't afford the analytics that are already out there available through hardware analysis.
Thanks, Chase. Now we want to discuss how our project works with regard to the data flows, including our stretch goals. From the figure seen, step 1 is the feeder relays, substation relays, and recloser relays that feed our device marked with POC, proof of concept, with data. This data is sent from inside the substation firewall to the CO, central office, servers, using step 3, the pre-existing communication links to the central office. At step 4, the CO servers run a service we designed that will prepare the data and analyze it with our machine learning algorithms. This analysis is what is submitted to our web solution, which will be discussed in more detail by Jamie.
Thanks, Patrick. Once the fault is analyzed and classified, it is then added to the central office server fault database. The central office server displays faults from the fault database in a graphical manner using Google Maps delivered through a web interface. This fault and other faults are displayed on the web interface using a heat map and other contextual labeling information to aid the protection and reliability engineer's situational awareness. The map will include an overlay of the electric grid as well. If the stretch goal of machine learning is successful, part of the information delivered through the web interface will be the cause of the fault. The fault will show up specifically in the location that the software has indicated using the calculated fault distance information. After the fault is committed to the database and displayed on the web user interface, it will then be sent off to the fault signature cloud platform. This part of the project is a stretch goal. The cloud platform collects anonymized fault information from all customers that subscribe to the service to continuously improve the accuracy of the built-in machine learning. This platform allows the software to learn from multiple utility entities and to continuously improve and recognize new faults over time. The cloud platform will be built using cloud-native methods to allow the product to easily scale to meet any need. Once the fault data has been analyzed by the cloud platform, an improved machine learning capability will be available to download to the customers. If the customer chooses to download the improved machine learning capability, the customer can choose to granularly release the improved capabilities to the proof of concept devices in the field if they are being utilized to perform the machine learning calculations. That does it for the fault protection data flow. Now we move on to Patrick, who will cover the current planning phase and the technical aspects of machine learning related to our project.
Thanks, Jamie. Now I'm going to discuss the current status of our project. I'm going to go from the planning phase and into the machine learning technical aspects of the project. So first, decisions made regarding scope. We considered a myriad of design options. However, our team's scope targeting was made much easier when we decided on an assumption. The customer will deliver circuit information and the fault data to us. Before this, we'd considered equipment on distribution poles for extra circuit insight and equipment in the control room of the substation to analyze and communicate back to the company. We decided that developing this metering communication component would detract from the real substance of what we want our project to be, which is identifying cause and location of faults. so we left these for stretch goals. There are a lot of reasons a web-based software solution was so appealing. It enables a cloud stretch goal for data mining extra data sets for training future and better algorithms to be more accessible. And it keeps us honed in on our primary focus. Also, our only real expenditure is man hours, which is nice. Now on to machine learning. I'll discuss machine learning steps in a little more depth. We're currently in the stage of selecting exactly how I'll be using this powerful tool, and we're considering Keras, PyTorch, and MATLAB solutions. This is while we're continuing to build our data set of fault information. As of now, we are planning on standardizing fault data and looking for trends in how the sine waves change due to known issues with sine wave analysis using ML algorithms. Now, off to Jamie to finish off technical considerations.
Thanks, Patrick. The central office server will consist of two primary services. These services will be split into modules called containers. The first service will be the web application and database that contains the fault information and displays the fault information to the protection and automation engineers. The service will be built using modern frameworks such as PostgreSQL database, Node.js web service, and a React.js front end. Google Maps will be integrated into React.js to display a modern and responsive web service. The second service will be the stretch goal machine learning platform. This service will use Python as the programming language and either Keras or PyTorch to perform the machine learning. The machine learning service will take structured fault data as an input and output structured classification data such as the cause of the fault. That wraps things up on the technical aspects. Now on to Shannon for the conclusion.
Thanks, Jamie. As discussed, the problem we are trying to tackle is the issue with fault data and fault gathering by local utilities. Our ultimate customer, we assume, will be the small utility boards and the local utility co-ops that are throughout the rural region. In order to do this, we intend to use machine learning to detect, analyze, and classify faults. Currently, we are working on the scope of our project, and we have narrowed it down to where we want to use machine learning and to be able to produce a viable heat map that will be valuable for these co-ops and these utilities, determine where the faults are located at, where they happen the most, and where they should send their trucks and teams out to repair early before something else big happens. We continue to grow our use of machine learning and our knowledge of machine learning to do faults. Our vision for this is to use a cloud-based, web-based application where multiple utilities will send in their data in order to better help each other. One fault from one company could help a fault at another company be discovered or analyzed before it actually happens.